Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is low voltage circuit breaker ground fault protection utilizing primary injection test method. My name is Michael Fleischer, and I'm the digital marketing specialist from Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Daniel Carreño, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Dinesh Chajer, Technical Support Group Manager, and Jason Aaron, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Daniel.
Thank you, Michael, and good morning to you. Good morning to my colleagues, Dinesh, Aaron, and of course our audience. This is, of course, the last installment of the Testing Tactics webinar series, and we're glad that you are able to join. Of course, we hope that you find this information useful. Okay, as Michael mentioned, we're going to discuss how to test the ground fault protection testing on low voltage circuit breakers with the primary injection method, right? I'm going to start with the reason behind this, of course, talking about the standards, right? In those documents that will give us the guidelines for this tests in the field. We're going to cover some of the basics to understand, the types of ground fault protection schemes, and again, why we are using this method to test them. And we're going to go on the step-by-step or the requirements to run these measurements in the field, as well as the challenges. That we'll face some challenges when trying to perform these tests, and of course, if we know those, if we know how to tackle them, of course, that will make us easier, right, in the field to be successful when we need to test this type of protection on those circuit breakers. So let's go ahead and start again with standards, right, the documents that discuss this topic and why this is important. And I'll start with the NFPA 70, right, the National Electric Code, which until 2014, right, when we reviewed this section of the code, and more specifically, Article 230.95, right, with the requirement for ground fault protection and with the requirement to test this protection element in my breaker again until all the way up until 2014. The recommendation from this standard, which of course is really important, is that the testing itself was left to either manufacturer or contractor recommendations, right? Oftentimes, this left this decision to the contractor, and again, a lot of times this ended up being just ourselves or the individuals in the field just going to the trip unit, pressing the trip button, the breaker trip, yes, our protection or the ground fault protection is working. So that was changed in 2017, right? So this latest or version 2017 of the NEC changed this clause C of that article, and now it requires us to test this ground fault protection element with primary injection method, right? So really big changes in the sense that now it's a requirement for us to test, and not only that, but it gives us special or very clear instructions on which method to use for the measurements. Again, so it's primary injection. If we look at the NEMA AB4, right, another very important document when it comes to low voltage circuit breakers. We still see the same recommendation as the previous versions of the NEC, right? Going to or leaving that decision to manufacturers primarily. And if we look at the NEDA documents, both the acceptance testing standard and the maintenance testing standards, very similarly to the NEC, it detects that we should use primary injection to determine both the ground fault pickup and the time delay for this particular protection element. It goes into details, into telling us that to verify, for example, polarities of the CTs involved in this protection element. And again, will give us instructions to test both the pickup and the time delay. It will also give us guidelines for the results, right? And basically, we can categorize those in two. The trip test, for which conditions the circuit breaker should trip. And that basically, as you can see in the current slide, is when the current direction is in the same relative uh, or in the same direction relative to the polarity marks of the two CTs involved in the test. And then we have the no trip test, right? So the circuit breaker shouldn't operate when the current direction is opposite relative to those polarity marks in the two CTs involved in the test. So again, we can group the measurements on trip tests and not trip tests. We're going to look into the detail how to make connections and a little bit more detail on what to expect, how to perform these two types of measurements. Of course, we have the pickup, right? We need to determine the pickup value for this protection element. And again, NEDA dictates here that this pickup value should be between 90% up to 125% of the setting, or up to 1200 amps, whichever is smaller, right? Which is really, really important. If we read carefully, we'll know now that if, I mean, for those breakers that have a higher current rating, no matter after I um, go above certain threshold, I still will look at the pickup value to be a maximum of 1200 amps. This is really important to keep in mind. I'll explain why in a couple of slides. For the timing, of course, then it will refer to either manufacturer specs, or will refer back to the NFPA 70, the NEC, saying that the timing shouldn't be longer than 1 second at 3000 amps, right? So either manufacturer or back to the NEC. So that's basically what we have in terms of standards. Again, the requirement changed in 2017, making the test now mandatory for those breakers that have this protection element, and that we have to perform it with primary injection. So let's go now to our next section, which is basics of ground fault protections. Of course, our objective today is not to discuss the ground fault protection scheme itself, but I wanted us, to be in the same page for us to be able to go into the testing portion. We'll have, or there are several different methods to detect this type of fault, or to sense this type of faults in the system with our circuit breaker. As you can see, we have the residual sense configuration, either 3-pole or 4-pole. We also have the option to have an external neutral CT, the zero sequence, and the source ground return. We're gonna focus in these two, the 3-pole residual and the 3-pole external neutral CT. Why? Because those are the most common types of configurations that you'll find in the field according to our experience. So that's why we're selecting those two to go and review the testing method. Okay, so 3-pole and an external neutral CT. Now, when we perform these measurements, understanding the CT polarity and the proper external neutral CT in case we have one, like in the example I'm showing you now in the slide. This diagram, I took it directly. I don't know if you can see the Micrologics 6 label in that box in the middle. So directly from a manufacturer manual, and actually that section of which I took this diagram explains the external neutral CT connections, right? And this particular example, the manual will tell us that if the supply is via the bottom, then you have to wire, as you see the external CT here, the CT a certain way, and of course if the supply is at the bottom, you have to not only reverse these connections but also change certain connections here for the control. So really important that again we understand the CT polarity and the proper connections according to the manufacturer specs. Of course, this is extremely important to follow, especially when we are doing acceptance testing, right? To have those manuals available and again, carefully review the instructions for wiring in case we're doing those, or if we are checking that the wire we didn't do the wiring, but we're checking that that is correct. Again, of utmost important that we have a good understanding on those connections. When we look at the settings, right, again, using the same trip unit, Micrologic trip unit, this is our panel, right, for the settings of the breaker. So we're gonna make a zoom to the settings for which we're gonna be able to change the settings for pickup and time delay of our ground fault protection element. I'm going to zoom since I think it's a little bit small. So you can see here at the bottom of those dials, I have my ground fault section. So the first one on the left, right, the dial with the letters from A to J will determine our pickup value. And the second one to the right will determine our time delay setting. So let's look at how that is shown in the table. If we go to the manual for that trip unit, I'm going to make a zoom as well, just to make sure you are able to see it. You remember, right, on the pickup dial, I have, again, positions in letters from A to J. And as you can see, I have basically four ways or four rows here in this table, and that I select the proper one for my record depending on my nominal current. If my nominal current, as you can see in the second row, when I'm zooming in, I don't have a pointer, 1 second. In the second row here, if my nominal current is below or equal to 400 amps, well, depending on which position I'm in, then it's going to be a multiplier, right, for my pickup value. So if I'm on, let's say on A, then my pickup value is 0.6 times my nominal current. And of course, the same applies if my nominal current is between 400 amps all the way to 1250, then I will use the second row. But now something interesting happens when I go either 1250 or above, right? When my nominal current is either 1250 or more for my circuit breaker, then that dial stops being a multiplier. If you see, now it's actually a pickup value in itself. If I'm on position A, as you can see in the table, then my pickup value is 500 amps, and so on and so forth. And if you remember that slide that we saw at the beginning saying that it's either 125% of nominal or 1200 amps, whichever is smaller, this is reflected here in this table, which again is taken directly from an actual circuit breaker manual. And again, as you can see, no matter what the current is if it's above or equal or above 1250 or 1250 amps, the maximum peak of value for ground fault protection will be 1200 amps. Okay, so really, really important. And of course, this applies for all bugs with this protection. And of course, I have the section of the table that will also detect the time delay configuration for this breaker. So of course, I have to take note of these two before I go and perform the measurement. So make sure you check them. And of course, when you look at the results, when you look at the timing, depending on which position you are for the delay, you will be pretty much selecting a curve from the time current curve in the manual or the one that the manufacturer provided for that particular breaker. So for results analysis, of course, right? So those are again the concepts and the factors that we have to check in the circuit breaker in the configuration to understand what we need to measure and how we analyze the result, which in terms of analysis is pretty much comparing right our results to the time current curve to see if they fall within the acceptable values. But so let's go ahead and talk about the testing itself, right? And I've mentioned a few times now that per the NEC, per NEDA recommendations, we have to perform this by the means of a primary current injection method. So what is primary current injection, right? Again, just to make sure we are all in the same page, right? Um, why is it called primary current injection, right? Well, with this method, we're pretty much emulating field conditions, right? And by that, I mean we're duplicating, we're using the same current values as the circuit breaker will experiment in the field in service in case there is a fault of that nature, and of course the breaker has to trip. Why do we have to use this as opposed to, for example, a secondary injection where that method will be pretty much simulating, right, as opposed to emulating the field conditions, right? If we use secondary injection, we're just simulating or replicating certain conditions, but not duplicating the conditions that the breaker will again experience in the field. And again, the importance of using primary injection lies in that when you duplicate those conditions, you're pretty much again using the same current as the breaker will see in field conditions in a controlled environment. Of course, you will be able to verify all the components of the circuit breaker involved in that operation, right? As you can see here, the of course the mechanism, the main contacts, the ion chambers, the trip unit itself, the terminal connections, right? Which of course it might sound that is a really simple thing to check. We can of course do contact resistance as an extra layer of testing for my terminal connections and main contact system of the breaker. But again, in the case of a ground fault, we want to make sure that the circuit breaker will be able to interrupt that high current. So using this method we will be using all elements of the breaker involved in operating when this condition is when this condition happens in the field. Now for connections, right? If you have been performing not only ground fault protection testing on circuit breakers, but all the others, if you're testing just the braking capabilities of the breaker for short circuit or for your long time or short time elements, you'll find the connections pretty familiar, right? You need, of course, a current source, and you can inject the current on each one of the phases to perform the measurements again phase by phase in the case of a three-phase breaker. And for the not trip, you'll have to connect a jumper in between two phases. And I'm of course showing here the different uh, connections depending on the type of sensing configuration that you have for your circuit breaker. And again, you'll find these connections pretty familiar, and if we even pay closer attention, you will see that the trip and not trip uh, connections are actually reversed as when you are testing again either your long time, short time, or in instantaneous for those breakers that have the ground fault protection element either enabled or integrated in the breaker. So again, pretty familiar connections when we talk about circuit breaker testing with primary injection. So let's go ahead and look at the trip test in more detail. Again, we saw the connections. I'm showing them here again. Pretty straightforward. We only connect to one phase of my breaker. It is the same if I have the 3-pole or the 3-pole with the external neutral CT. And we first have to determine pickup, right? There are two ways to do this, either using the pulse method or the run-up method. If you use the run-up method, right, used of course a lot, you will pretty much will start injecting. Of course, you know, right, that what is your range of current that you expect because of you checking the settings of the breaker or of the trip unit. Of course, you start injecting again in that range, but you do a continuous injection, right? So you have your instrument, you start the injection, and of course you have manual control of that current, and you can slowly go up until the breaker trips. And of course, whenever the breaker trips, that's your pickup value. But there's or we prefer the pulse method. Why? Right? As I said, when you do the run up, you're continuously injecting current. And of course, right, when we do that, we're gonna start, I mean, we're passing a current through our circuit breaker, and of course, we're gonna heat the conductors of my circuit breaker. And of course, that can change the tripping characteristics, right? We also have our thermal protection. So that's what we prefer, or we recommend to use the pulse method. So rather than using a continuous injection, you can configure your instrument to do pulses, right? And most instruments, or if your instrument allows, you can in the settings say, okay, I want to for when I do momentarily or pulses injections, I want to use 10, 20, 15 cycles. So when you use that method, we recommend starting at 70% of the pickup, you do a pulse. If the breaker doesn't trip, of course, you do a step in current, you do another pulse, and so on and so forth until you find your pickup value. That way we avoid hitting the elements, the protection elements of the breaker, and again, changing the tripping characteristics or influencing that and getting a not so accurate result for my pickup, right? So again, the pulse method is preferred to determine that. Once we have the pickup, then we can go on to determine the time delay, right, for each pole. And we can start by using 150% of that pickup value. Of course, then you will do a continuous injection. You can configure your instrument to inject for, of course, longer than the delay setting. Just make sure, of course, that you cover it in case the breaker is tripping after that. And again, you use the continuous method. And once you have your recording, as we saw before, you can compare against your time current curve for that breaker. Going on now to the no trip test, right? Then we already have the pickup. Our connections will be different, right? And again, if we compare these connections, as you can see, we have to short or use a jumper, right, to connect two phases in series, as you can see, both for the no trip and I'm sorry, both for the trip pole and the external neutral CT. You use the two phases, or in the case of the neutral, you use the neutral as a return pad. And of course, on these tests, we expect that the breaker will not trip. What are we accomplishing then if the breaker will not trip? Well, a really, really important objective of this test, right? We also use 150% of pickup setting for longer than the time delay, right? And again, if the breaker is not tripping, what are we measuring? Well, we are making sure that the CTs of the circuit breaker are installed correctly. By installed correctly, I mean phase, the polarity is correct, and also the size, right? I'll cover in a little more detail in a couple slides. And actually the next one, which is the sizing. We, as I mentioned, we verify the polarity, but also the size, or more technically the ratios, right? The ratios should be matched. And you can actually perform an extra test, which is the one I'm showing you right now. And on this configuration, as you can see, the connections are a little bit different in the direction, right? If I go back to my previous slide, then I am actually injecting the current in the same direction, right? And what you will have to see here is that for whatever your test current is, if you look at the trip unit readings, the current reading should be twice of your test current. Again, purpose of this test is to verify the ratios of the CT, which should be matched. Also, of course, really important for proper operation of this protection element. So those are basically the measurements that you have to perform. Again, not difficult. I mean, if you are already familiar with testing the other protection elements of the circuit breaker, uh, testing the ground fault protection, again, is just a matter of knowing the proper connections to perform, and of course what to look for and how do I analyze my results, which again, really simple, comparing my values against the time current curve. And in the case of the external neutral CT, well, again, the phasing, right, the connections, the polarity, and the size are the two parameters that I need to make sure that are both installed correctly and in good working condition. So what are the challenges? Right, it sounds pretty simple, but what are the challenges that we will face in the field when we are performing these measurements? First, the power source for our instrument. Ground fault protection testing is probably special in the sense that, yes, we need a primary injection instrument, and we're going to look at that at the very end of the session. The good news is, I mean, yes, it's a primary injection unit, but it won't be a huge or really large. So is a little bit less of a concern as opposed to when, for example, testing my short circuit or instantaneous protection element of my breaker. But still, you want to make sure that you have a proper power source to energize your instrument, your test instrument, right? That either if you're turning off your building circuit, right, or your facility circuit, or if you're using a generator, an inverter, especially important, right? You want to make sure that either that generator or that inverter has the proper power quality, right? Remember, most of these instruments, well, of course, you are stepping the current up, so you have a transformer inside it. If you're feeding with bad quality power, well, you will get something really similar, or pretty much that you will get that in the output, and of course that can affect your results. So again, make sure the power source that you're going to be using is it's yeah, properly sized, and again, in terms of power quality, that you are sure that that won't affect your test results. breaker configuration, right? Starting with the connection method, either top fit and bottom fit. Why is this important? Because of access. I'm going to show you a few pictures later, right? Especially when we talk about power circuit breakers, which is my next point. Access becomes also again a challenge, something I need to review, be mindful of before heading out to the field. Maybe I need longer cables or certain special provisions to be able to connect to my terminals of my circuit breaker. Features, right? Again, especially when we talk about power circuit breakers, thermal memories, some selective interlocking, some switches or under voltage coils that will have to be energized so you can actually perform the measurements. Again, of course, important that you are aware of those in case you need to work with those switches. Defeating in some cases you shouldn't, right? Especially in facilities that are already, if you have only a section isolated for you to work, again, make sure that you can work with those switches. And again, if you need external um, power sources, which is my next point, the trip units, right? Sometimes you need either external power or a secondary injection tester. For some breakers, this secondary injection tester is a device that typically the manufacturer of the breaker provides. And again, sometimes that is actually needed for you to power up the trip unit, change certain things to put it in maintenance mode so you can actually perform the measurement. So really important that you investigate that before heading out to the field and take the measurements. Connections, of course, we have the options of using cabling or bus. And of course, as we mentioned, right, when it pertains to ground fault testing, we already established that no matter how well, if we are dealing with breakers of with nominal currents of higher than 1250, the maximum current that we will need for this particular test is 1200. So that makes it easier, right? We now can say that, but cabling is preferred for ground fault testing, right? It's easier to connect to manage in the field. So, and because again we know for a fact that the maximum current that we're going to be testing with is 1200 amps, then again we can establish that cables will be enough to perform these particular measurements. The length also becomes an important factor to consider, right? Um, as well as thickness, right? Of course, our connections from our instrument, as you can see in the picture, to the breaker, those cables that I'm using to connect to the breaker will be part of the circuit connected to the output of my unit, right? And the impact that it has is, of course, impedance, right? Which is my next slide. We want, of course, to minimize that impedance so we can actually achieve our current, especially when we talk about those larger currents, that in our case, 1200 amps. If you are ever in the field with your instrument where you're performing, and of course this applies not only to ground fault testing but primary injection in general, uh, whenever you are having issues achieving your test, your desired test current, there are certain steps you can take to minimize the impedance of that circuit. And of course, first I already mentioned, right, the length and the thickness or the cross-section area of the conductors you're using is a big factor. Of course, the longer the cable or the bus is, of course, the bigger the impedance will be, and the thicker the conductor or cable it is, the lower the impedance will be for that particular conductor. So either you can shorten the length of those cables or increase the size of them to reduce the impedance of that circuit. Really important when you are using especially cables, avoid loops or windows, right? Arranging them in a way that you are creating a big loop or a big window in between the two conductors, or as I'm showing you in the picture, right? Sometimes because of the test current, we actually need to use two, three, or more cables on each connection to, because again, the current that we are utilizing for our test. If that is the case, you can actually twist them. And let me zoom to this section in my slide. When, and of course, a really easy to follow recommendation, right? But also really easy to make it incorrect. As you can see, and just for the clarity, we use two colors here. And if you see on this current box that we have at the bottom, right, we have the polarity mark on the left with the black dot. And those two conductors that go out from that side of my current box are black. On the other side, I have gray cables. And when we say, okay, you have to create twisted pairs of those conductors, we mean that you have to take one conductor of each side of your current box to create those twisted pairs. Again, oftentimes I've met it many times, especially when I have more than two cables per connection. It's really easy to get it wrong and twist two cables from the same side of my current box, which will accomplish nothing in terms of reducing the impedance. And again, really easy in the field because I would say 99% of the cases, our actual test cables are not color coded on each side, right? All of them will be the same color. So be mindful of this. You have to create these twisted pairs with cables, in technical terms, with cables with the current direction opposed to each other. So that's how we reduce the impedance, neutralizing the flux that those currents are creating right around the cable. So that's why we need cables from opposite sides of my current box. So that's how you, again, some tips, some recommendations to minimize the impedance and achieve your test current in case you're having trouble achieving it. Right, access, as I already mentioned, right, especially with power circuit breakers, really important to take into account having the correct length of cables, the accessories needed to connect balls or vice grips or clamps to connect to the breaker. Uh, some examples or some pictures of those secondary trip units needed to be able to test certain breakers, like this one I'm showing in the picture, right? So that's why we have that port in my trip unit to be able to connect that secondary injection unit and be able to enable the circuit breakers for maintenance testing. Connections, as you can see, as I was mentioning, right, the length of the cable. In this example, we're using vice grips. Also really important, let me show you a couple more, either vice grips or clamps. Of course, we want to make sure that those connections are tight, that the contact resistance between my cable, my test cable, and the circuit breaker terminal is minimized. And again, sometimes we use bolted connections, preferred, but yes, it will take a little bit longer. We need the hardware. So sometimes we recur to, again, using vice grips or clamps. You just gotta make sure that you don't damage the terminal of the circuit breaker, right? Which, I mean, easy to do, especially with vice grips. So be mindful of that as well. Couple of more examples, in this case connecting to the external neutral CT, right? You can see the jumpers here on the picture on the left, right? To connect to the neutral of that circuit breaker. So that's pretty much the challenges, and I want to use the last few minutes of my presentation. We're nearing the end of the presentation, just to talk about the SPY 225, right? So obviously a primary injection test unit. And if you know the Megger portfolio, of course, it is not the only unit that we have for primary injection measurements, right? We have a very wide, I'm showing here only, let's say, the representatives of each families, right? Our primary injection portfolio is very wide that you can see. We have units um, from 500, 900 amps that go all the way up to 60,000 amps. And of course, we have the SPY, which maximum short circuit is 2000 amps, right? And it's a new generation type of instrument. So I want to give you some details on why I say it's a new generation. And of course, right, the capability of the SPY being able to inject up to 2000 amps um, makes it ideal. It wasn't designed with the ground fault protection testing. Specifically, you can actually run all the other measurements on low voltage circuit breaker rated up to 225 amps, hence the name. But again, we saw that maximum current needed for ground fault protection testing is 1200 amps. So that makes the SPY ideal to 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 have if I'm running this type of test. Why I'm saying that this is the next generation of primary injection testers? Well, we know that the high current capability, and even we can get up to 2000 amps. It is the smallest primary injection system in its class, and the output current regulation control is really important. So let's look at that in a little bit more detail, right? So starting with automatic regulation and the current decay elimination, right? Especially when we are running those long delayed test. We start with a continuous injection of, let's say, 1000 amps, and as we mentioned, right, we're going to start heating up the elements in my circuit breaker, and that will make the impedance change. So typically that results in current decay. So you get if you look at the current in a oscilloscope, you can see that the current will actually decrease. Well, the SPY is always uh, monitoring the impedance of the circuit, and it will adjust to keep the current constant. You also get the DC offset elimination, so no more, and that is automatic. You don't have to change anything. All you have to do is, sorry, here when I went ahead. No configurations, no more fiddling with the firing angle. The unit will always make sure that no DC component is present in the output. So you make sure that whatever you get in the ammeter reading, that's what the unit is injecting. Although not useful for ground fault protection, the system can, or a SPY 225 can be parallel or series connected with up to 4 units to increase either the current or the open circuit voltage capability. If you're familiar with PowerDB, right, our prime power or testing management software, that is what we use to control the SPY, either with that computer or with a dedicated touch view interface. So, and the software looks and behaves the exact same on, again, both the SDVI or the computer. When you use the dedicated software, the dedicated form or virtual form for the SPY, the software has or includes thousands of time current curves for circuit breakers, right? So that way you don't have to take the PDF or even the printout to check and manually review your results. The curves are integrated, and the software will actually plot the result in the curve, and it will automatically tell you if that is a pass or a fail for that particular breaker. If the circuit breaker you're testing is not in the library, of course, you can send us a PDF. We'll digitize it and include it in the library for you. And as I already mentioned, the report is automatically generated. So pretty much ready to save as a PDF or print in just a couple clicks. And with that, I will send it back to Mike to go over the questions round.
Thank you, Daniel. So at this time, the presentation portion of our webinar is officially concluded. We'll now take some time to answer as many questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar on January 15th, titled Fundamentals of Transformer Commissioning and Maintenance Testing. Now let's get to your questions. The first one I have, I'm going to direct to Dinesh Jajer. Dinesh, at which voltage level do breakers require primary injection testing? Under 2.4 kV?
Good morning, everyone. It's a good question. So usually, as per IEEE and NC qualification, we have defined the breakers into low voltage circuit breakers, medium voltage, and high voltage circuit breakers. And primary injection is typically reserved or utilized for low voltage circuit breaker. And as per IEEE, any breaker with a voltage rating of 1000 volt or less are considered as low voltage circuit breakers. So it's a quite industry practice that people would use primary injection testing for any voltage or any circuit breaker rated less than 1000 volts. And one other point I would like to mention is that when you are doing the primary injection test, you are performing the test at high current and low voltage level. Usually the output voltage from the instrument is anywhere in the range of 0 to 6 volts. So it is not a destructive test. The cases when they are doing qualification test at manufacturing sites, that's when they do these destructive tests where you are applying the high voltage and high current at the same time. So just think about a circuit breaker in operation. It may have a 480 volt service or whatever the voltage level is, and at that time, if a if a fault happens, then the current would be in hundreds of amps. So in those situations, you might be dealing with high voltage and high current at the same time. But this test, this offline primary injection test that we are talking about, is not a destructive test because you are using low voltage and high current concept.
Thank you, Dinesh. Our next question is going to go to Jason Aaron. Jason, is the 90 to 125% tolerance for the pickup test based on manufacturer recommendations?
Okay, good morning, everyone. And this is a good question to kind of emphasize a point that Daniel brought up in his presentation when he was talking about the ground fault pickup testing. And when he talked about that test, he said that it's preferred to do the pulse method for that test. So basically, you want to sneak up on it as you increase your current level and apply it to the device until it trips. And this 90 to 125% tolerance for that value comes from the NETA standard that Daniel referenced for both the acceptance testing standards and the maintenance testing standards. However, it is important to understand that there are manufacturer specifications whenever it comes to these systems. So it's really important to understand what the application is from the manufacturer, because they may have a slightly different tolerance. However, in the absence of those tolerances, that's where these NETA standards come in, so that you have a guideline to go by whenever you're performing these types of tests.
Thank you, Jason. Next, back over to Dinesh. Is primary injection required both by the manufacturer and in the field at its final location?
So it's a very interesting question, because the answer, which we don't like to hear, is it depends. So when you start talking about manufacturer, what they would do or they might do is that they might do what we call a type test, in the sense that if they won't perform this primary injection testing on every single breaker, but they might perform it on a certain type of breaker, a certain type or model of the breaker, and use that as a reference measurement for all the breakers of that class and model. So that's very standard. Usually you don't get the manufacturer's test results. Typically you would go and ask for it and those kind of things. So that's not very common. Now, primary injection, as Daniel mentioned in his presentation, that when you have a trip unit on it, or the breaker is a thermal magnetic breaker where it has brains and power at the same time, or in the same body, or in the same configuration, in all of those cases, primary injection is the right method, or is the only method that can check not only the trip sensing capabilities, or whether the breaker would trip or not, and in addition to that, it would also check that whether breaker would indeed trip or not. We also have methods like secondary injection methods, where you only check the brains of breaker, where you just send a signal to the trip device, and if the breaker, if the trip device or the trip unit operates, we know that we assume that the breaker would trip in real life conditions as well. But primary injection, as I said, like, it tests both, and because of that reason, when you're doing commissioning testing, or when there is an outage at a data center, hospital, it is typical of technicians and engineers to perform primary injection test. And there are some other tests that go along with this, like insulation resistance, low resistance measurement. So those are some of the other tests that you would do on breakers, low voltage circuit breakers. But coming back to primary injection, it's a very standard test that is recommended during commissioning and maintenance, just because of the value that it provides.
Thank you, Dinesh. Next, back over to Jason. Jason, what is the TCC?
So the TCC is the time current curve, and the time current curve is comes from the manufacturer of whatever device that you're testing, whether it be a ground fault relay on a voltage pressure switch, or or a circuit breaker with the external neutral CT, or whatever the application may be. That Daniel gave many different examples. And what that time current curve has is it's a plot of the interrupting times for an overcurrent device based on a given current level. So, and Daniel brought one up in the presentation. I think it was on slide 17, if we can see that. And basically what that's going to do is, based on the amount of current that you apply to the device, it's going to tell you how fast that device is going to operate, or how fast it's going to react at that current level.
Thanks, Jason. And while I have you, if the main breaker is connected to a utility transformer, does it need to be disconnected from the main breaker in order to do the GF test?
Well, the short answer to this is no, it doesn't. As some of the examples that Daniel gave whenever he was showing how to connect the test set, all you really need to do is to connect the device in that manner and ensure that the current flow that you have while you're performing the primary injection across that system is applied properly. However, it is important to mention that if you do have some type of secondary scheme where this may communicate to another device within your protective system, you need to understand what that is before you perform this test, because if you have some type of scheme where the device that you're trying to test trips, may communicate to another device and then trip something else in your system. While this test is done with your system offline, it is important to make sure that you're not going to trip something that's in the system that you don't want to take down.
Hey, Jason. Back over to Dinesh. Dinesh, what size and quantity of cables can the SPY unit take?
Uh, I think that's a very good question, because I guess the person who asked the question must have performed this kind of testing out in the field, because the size and the length of cable would directly impact the amount of current you can get out of the test set. And as you guys know that and Daniel did cover that, where he covered the impedance of the circuit. Let me kind of give a little bit background, so that way we can understand the question better. So every instrument has a certain open circuit voltage, and the length of the cable uh, going to the breaker and returning back, that whole circuit, one-way length, breaker, contact resistance, and the return path of the return cable, all of this is the impedance connected to the to the to the test instrument. And for all practical purposes, the impedance of the cable is much greater than the resistance of the breaker itself. So if you have longer length, then you are increasing the impedance of the circuit. And as you know, that current is a function of voltage and impedance. So if I have higher impedance in the circuit, what it would do is that it would reduce the amount of current you can get out of it. So the length and the size of the cable is very important. And as you guys may know, that the formula for resistance is rho L over A. So longer the length of the cable, higher the resistance would be. And it is inversely proportional to the area of cross section of the cable. So if you use thicker conductors, then it's very obvious that you would reduce the resistance. And if you reduce the resistance, you can get more current out of it. So now I will come to the question that says that what size and length of the cable is recommended with the SPY. So SPY can give you 2000 or 2200 amps of current, and that current is recommended based upon using a 4-aught cable with a 2 feet length one way. Now, if you decide to increase the length of the cable and keep on using the 4-aught cable, then certainly, as you would increase the length of the cable, the amount of current you can get out of the instrument would reduce. And that's true for any test instrument, let alone the SPY unit. So with 4-aught cable and 2 feet one-way distance, that's the cable that it comes with, and you would get 2000 amps out of it. There are cases where what you can do is that you can put multiple conductors together in parallel. That would further reduce the impedance, and then you can increase the length of the cable to offset the reduction in the current. So we have seen cases like in nuclear power stations where they have breakers on different floors. People have used like 10 feet of length, 15 feet of length, but it would come at a compromise of reduction in the level of the level of the current you can get out of the unit.
Thanks, Dinesh. I'm going to send this question over to Daniel. Daniel, could you explain a little more on the slide where you mentioned the current would redouble, and why is that?
Sure. Thank you, Michael. Let me go back to the slide. what is it? This one. I think this is the one you were referring. And it has to do with how the protection element works. If I also go back, I think it was the slide on NIDA. One second. Most of the sensing configuration use a system or a system type of summation, right, which is looking at the currents you see here in the first point here in the slide. And I'll go back here. So the system is monitoring the currents on all three phases and the neutral, right? And depending on the direction of currents, that's how the system can determine that a ground fault is present, right? So for this test, if you remember, if I go back to my previous slide, if you see the direction of the current for the node trip is opposite, right? If you see the breaker, we're incoming from the line, getting out of the load, and then on the neutral, we're going from bottom to top. So when we do the sizing test, and that is the purpose of this test, is we inject the current in the same direction, right? And again, because of the summation type system, the trip unit will redouble your test current because it's pretty much adding the two values together. And again, that's how, on this case, you determine that the ratios also are properly installed for those two CTs involved in the measurement.
Thank you, Daniel. Over to Dinesh. Is there any application note that shows the ability of the SPY 225, or sorry, yeah, 225 to connect four units together for higher current application?
Uh, uh, Again, that's a very interesting question. Daniel covered that part as well. Yes, we do have step-by-step instructions to show how we can connect four spies in parallel to get I guess 4 times the current out of the unit. Just to give you an idea, the way it works is that you have 4 units, and each of the SPY unit have Ethernet ports on it. And what you do is that you stack all the 4 SPY units together, one over each other. And then what you would do is that you would do a daisy chain connection of Ethernet from one unit to the other, second unit to the third to fourth. And then the first unit would become the master unit. Other 3 units are the slave units, or you can just now then think of those as current boxes. That's all. So you would communicate with your computer through to the first unit, and then the output terminals of all those 4 units would be tied in parallel, and then from there you would connect to the breaker. And again, as I said, like it's a master slave configuration, and then you control the master unit, and then these 4 units interact with each other to give you the desired current. Now, the nice thing is that let's say you want to get 5,000 amps out of it. So you are only gonna enter your target current, and then all the 4 test set would do whatever needs to be done to get that required current. And Daniel also mentioned one of the thing, which is that these SPY units have what we call as a feedback loop. So as you know that as the test is ongoing, because of the heating of the cable specimen, the current would typically go down. But because we want to run the test at a certain level of current, there is a feedback loop where it would auto-regulate the current. So if the starting current was 5,000 amps, and now the current is at, I don't know, 4,900, there is a feedback loop mechanism where it would auto-regulate and bring the current back up to 5,000 amps. So it comes very handy where you don't have to manually adjust the current during the testing. So if anyone is interested in knowing how to use 4 units in parallel, just let us know and we can send you some documentation on that.
All right. Next is over to Jason. Jason, during the time delay test, is it standard to test the ground fault at different percentages, such as 300%?
So whenever we're testing the time delay for a ground fault system, it is important to perform these tests at different different time delay points. So whenever we do perform that test, you want to inject 200 or 200% and perform a time delay test, and then 300% and perform a time delay test. And the reason for this is typically you're going to see different values for the test results, and this is based on what we talked about earlier with the time current curve. If you look at the time current curve from different manufacturers for circuit breakers or a ground fault relay in the case of say a bolted pressure switch for a zero sequence application, your tolerances for your trip time is going to be different based on the amount of current that you inject. And that's why we do this whenever we do that test, to make sure that dependent upon the current level that the device sees, that it's going to trip within that required time tolerance.
Thanks, Jason. Over to Daniel. When testing, is it acceptable to test one phase to verify that the brains are working properly, or should you run the full test on all three phases?
Thank you, Michael. I would say, and I would recommend to run the test on all three phases. I mean, you're right saying that on each one of those measurements, yes, the trip unit is involved, and you're pretty much making sure that that is working. But remember, right, there are other elements, right, individual on each phase that will be involved. Just name a couple, right? The terminals, the contacts on each one of the phases, and the sensing element, right? The CTs, right? So you want to again make sure that all of them are in good working condition. So I would say it's always recommended to run the measurements on all three phases.
Thanks, Daniel. Back over to Jason. When doing maintenance testing, is primary injection recommended instead of using the manufacturer test set that only tests through the relay through the front panel?
So doing primary injection is recommended over doing a secondary type test using a manufacturer specific test set. And the reason for this is whenever you use that manufacturer specific test set and you do a secondary injection test, all you're really doing is testing the trip unit or the electronic aspect of the brains, if you will, of that device. You're not testing any of, you're not testing the mechanical function of the device, but you're also not injecting current through the CT of the system. So if you're not doing that, then there's several aspects of the system that you're really ignoring whenever you do that type of test. I mean, if in a situation where that's all you want to do is test the trip unit of the device, then sure, you can use one of those manufacturer specific test sets. However, if you really want to test the system and get a proper evaluation of what you have and have confidence in that system and actually tripping whenever you're going to need it to trip in the real world scenario, then you need to do this type of primary injection test to verify that the system is going to operate properly.
Thank you, Jason. To Daniel, for 6,300 amps low voltage CB, what would the test current be?
Thank you, Mike. And we'll go back again to one of my slides. Important to take into account two things, right? This is from NIDA, right? For the pickup that remember, right? Even though when you're testing breakers like this specific question from our audience, right? A 63, I think it's 6,300 amps for rated current, our ground fault will not be more than 1,200 amps. So that is the maximum current that you ever need for this protection element, ground fault protection. And let me show you another part of my presentation here. This is again this table. I took it directly from an actual circuit breaker manual, the maintenance manual. And again, you see that for currents bigger than 1250, your dial for it stops being a multiplier and it actually becomes an actual value for current. So maximum is 1200. So for 6300 amps breaker, the test current will be 1200.
Thanks, Daniel. So Jason, how do you handle a self-powered type trip units where you need, for example, 30% of FLA just to turn on the trip unit? We run into this when trying to inject current through the neutral inline CT. Do you need two current testers?
So for this application, in the last answer that we gave, we discussed the secondary injection test set for different applications. And in some cases, you're not going to be able to push enough current to operate that device, or it's not self-powered where the CTs of the unit are going to operate that, power up that trip unit. So you're going to need that secondary injection device just to power up the unit. This is also helpful whenever you're changing settings on the system, so that it just makes it's just ease of use whenever you're changing the settings of the system between these primary injection tests. So it's not necessarily that you need two primary injection test sets, but you're going to, for this example, where the trip unit isn't self-powered, you're going to need that power supply to be able to power up that unit so that the system is going to operate whenever you do the high current injection test.
All right, thanks, Jason. To Dinesh, what is the frequency of doing these tests?
So I guess we talked about ground fault protection testing, and also your regular primary injection testing, which is, like your short time, long time pickup, those kind of things. So and also the CTs as well. So when it comes to the frequency of it, it's kind of difficult to pinpoint at a certain document. You can refer to NETA ATS, MTS. There are some guidelines in that NFPA. There is a NEMA AB4 document. So these are the places where I would go and look for. And also, depending upon where these breakers are located, is it a critical data center, hospital, is it at a nuclear facility? So that would also determine how frequently you would do the test. And when you start talking about utilities who may have these breakers at a number of different locations, they may have their own testing and maintenance program based upon the predictive maintenance or preventive maintenance that they might follow. So there is no straight answer on this one, but there are a lot of documents, there are a lot of guidelines that you can use to determine what is the right frequency or interval at which you should be performing these tests.
Thanks, Dinesh. My next question is also for you. My experience has shown it's not always possible to get a high current unit into remote locations. Should you have a ductor with 100 amp capabilities, would it be sufficient to primary inject at that level and verify metering on the trip unit?
So again, thanks for that question. The person who has asked this question certainly knows the challenges in the field. We are talking about a instrument that is not lightweight. SPY 2000 might be considered lightweight because you can carry in one hand, but when you start going into the instruments that can give you 5,000 amps, 20,000 amps, 60,000 amps instantaneous. These test sets are difficult to move around. So I certainly see the question why it has been asked. So as I mentioned earlier, that the right way of performing or checking the condition of the low voltage circuit breaker is primary injection. And when I say primary injection, majority of the breakers that we run into are AC circuit breakers. You would run into DC circuit breakers as well, but AC circuit breakers are the most common ones. And if you want to test those breakers, you would need AC current. So yes, you can have a ductor with 100 amp capabilities, but that's not what we are looking at right now. So you have two ways of performing the test. One is the primary injection, other is the secondary injection. Primary injection, we talked about it a lot. It's the most recommended method, but yes, moving things around can be challenging. And that's the reason why with the modular functionality, like a SPI helps a lot, where you don't have a one single piece that you need to take three floor up kind of thing. So that's an advantage with the unit like SPI. And the other method is the secondary injection method. If you absolutely cannot do primary injection, the only thing that you can do is secondary injection, then yes, you can go for the secondary injection method, but it will only check the trip devices, trip unit, the brains of the breaker. But if you truly want to check the muscle power of the low voltage circuit breaker, whether it has the capability to interrupt that level of fault current, if you want to check that, then primary injection is the only test that would do that.
Thanks for that, Dinesh. Moving on to the next question with Jason. Jason, how would you sell primary injection testing to a client? Why is primary injection necessary over secondary injection testing?
Okay, so earlier in the presentation, Daniel talked about standards and the requirements for the primary injection testing and kind of what changed in 2017. NFPA 70 and the NEC both mandated that the ground fault systems shall be tested by a primary injection process. Now, prior to this, it was mentioned that it was left up to the contractor or the manufacturer of the equipment on how to do these tests. Well, whenever you talk about primary injection testing, you're pushing current through the system in the same manner of a real world application. So you're testing the CTs of the system. You're testing the shunt of the system that's actually going to trip the device whenever you have that overcurrent condition for the ground fault or on your neutral. And whenever you do a secondary injection test, you're not doing any of that. So like Dinesh just said, whenever you're ensuring that the circuit breaker is going to have the ability to trip whenever it's under that ground fault condition, the only way you're going to do this is through a primary injection test. It's important to emphasize that while secondary injection testing is convenient, it's not necessarily an effective test. The only thing that you're doing whenever you do that secondary injection test is testing the trip unit or the brains or the relay of the system. So you're not testing your neutral CT. You're not testing the mechanical function of the device or the CTs that are on the primary conductor of that device. So for all these reasons, plus the mandate of the standards, this is why primary injection testing is required.
Thanks, Jason. Back over to Dinesh. What are the output power requirements to the SPI 225? If using 4 units, it seems like it could be difficult to obtain 4 input sources.
Thanks for the question. So the SPI 225 can operate from your regular wall outlet. It can take 120 volt as the input source or input voltage, or you can also use 240 volt of input power. So 120 volt obviously is very standard, very common for here in US, and there might be some places where 240 volt might be applicable as well. Now, on the contrary, I think that it's much easier to get access to 120 volt outlet with a 15 amp circuit or 16 amp circuit, contrary to like 480 volt 350 amp service. If you really want high levels of current, not every place would have 480 volt of service available. So with the SPI unit, and if you want to use 4 units together, there are two things that you have to keep in mind. One is that all the four SPI that you're going to use need to be powered from the same phase. So because we don't want any phase angles when we're going to trigger at time 0 all the SPI units. We don't want any phase differences between the currents coming from different SPI units. So one requirement is that they should be on the same phase. And if you are planning to max out the current, let's say I don't know, 2000 amps, at 2000 amps it might draw close to 15 amps from the input source. In those cases, you would want those 4 units to be on 4 different circuits, like 4 different breakers. And what that would do is that you won't trip the input breaker because you are maxing out the amount of current you can get from that wall outlet. But let's say you are only planning to use 4000 amps. Then you can put 2 SPI on one circuit and other 2 SPI on the other circuit, and you should still be okay. So it all depends upon the amount of current you're trying to get from the SPI units, and based upon that, you would decide how many circuits you would need, but all of them need to be on the same phase.
Thanks, Dinesh. It looks like we have time for one last question. I'm going to bring it back to Daniel since it started here with you. When primary injecting, would you test the breaker at its lowest settings to prevent stressing the breaker for an acceptance test?
Thank you, Michael. Well, this is a very good question, and one that we get a lot, together with the one that Jason responded to, I think, a couple of questions back about comparing or selling or selecting primary injection over secondary injection, right? Of course, we always worry about overstressing our devices when we perform these measurements, right? And again, we get this question a lot. We have this debate. We have had it many times, obviously internally and with customers. And yes, when we are testing with primary injection, we are stressing the circuit breaker, right? Because we're, as I mentioned already, the actual definition of testing with primary injection is duplicating the conditions of fault in service. So yes, you are stressing it. And when we dial back all to the lowest setting, I mean, we are pretty much proving that the trip unit, it is sensing correctly, right? That all the elements that compose the trip unit, right? The sensing, the current transformers, the control wiring, the logic in the trip unit is working correctly. But right, remember that when we're discussing circuit breakers, right, it's a protection device, and we have them there sometimes, a lot of times, to protect critical systems, right? That we don't want them to fail. That's again part of our protection system. when again when we dial back, yes, we prove that the trip unit is working correctly, but when the circuit breaker operates, when it has to interrupt a fault, right, it has to dissipate energy, and the breaker is constructed in a way that should be able to do this many times. And yes, it is a finite number of times. It is not no, there's no manufacturer that will tell us a circuit breaker will work indefinitely, right? It will actually, most of them will give us a rating of how many times it can interrupt a fault current, and we also even get graphs on depending on the rating or the actual fault current, how many operations we can expect that breaker to have or to perform its function correctly. But then we go into the again the debate of saying how critical this system is, that I want to be 100% sure that the breaker will be able to interrupt a fault current. So I think I hope I'm answering your question. As again, I would say it is valid, yes, but if it is a critical system, I personally would rather test it at the full rated capability, whatever the setting is for service. I would advocate to test the breaker at that setting, and depending on the criticality of the system it's protecting. And I don't know if the next Jason want to add something.
Yeah, Daniel, I would just add one comment, and what you said is absolutely correct. One analogy that I can give is that let's say you're preparing for a marathon or a race, and you have to run for 10 miles. And in your preparation, you say that, you know what, I know that this marathon, my target is 5 miles an hour, and it's a 10-mile race. So is it okay? Is it okay if I run only for 20 minutes at 5 miles? And if I can do that, does it guarantee that when the race or when the marathon is going to happen, would I be able to do 10 miles at the same speed? And that's exactly what this question is asking, that if you're going to test at lower setting, yes, it may pass, it might give you an indication that it may work, but when the race actually happens, when the amount of current that it needs to dissipate, the amount of stamina you need for the race, do you have that? Does the breaker has that capacity to dissipate the energy? You would never find out because you never ran the test. You never ran 10 miles at 5 miles an hour to check that. So yes, there is a probability that it might work, but that's a guesswork at that point of time.
All right,
Thank
thanks,
you, Dinesh.
guys. Yeah, it looks like that's all the time we have for our Q&A session today. We apologize if we did not get your question live, but we will be working to follow up with you offline. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great weekend.